This is 1 plus delta P. This is delta S. I want to see what is delta P over delta S. And that is your design parameters that you use to fit into Ramet, right? I'm sure you heard of Ramet algorithm, which is equivocal design. That's MATLAB. You can say help Ramet. You can see what's going on. What they want is what is omega P, what's omega S, what's the length, and what is the weight. Okay? And that's how we want to do it. We want to say that we want to figure out what could be the length of a half band filter. Symmetric, real coefficient. Can this omega P, omega S be arbitrary? Or is there any special properties that this is going to have? How it is weighted? Okay, so the question to you is intuition. Can this be arbitrary? Can I choose 0.1 pi and 0.7 pi? Why not? Somebody say no. Why not? Intuition. Why do you think that this cannot be arbitrary?
Quality of the filter. It is depend on the quality of the filter.
The quality.
If the rank is too large.
Okay. What if I have 1,000, 0.4 pi, 0.6 pi, and 0.4 pi, 0.5 pi? Would that be okay? Would length and the length 0.4, 0.5. Would that be okay? Think about this. You see that what you are given here, what is given back will be the impulse response and approximate that ideal response. Right? That's what happens, okay? There's a lot of constraint on this particular one. It's not arbitrary. In fact, the desire of freedom is half of the order. Right? If this is, let's say this is 7, right? That's 6, 5, 4, 3, 2, 1, 0, and so on. Okay? This is too big. Let me do 5. Okay? It's 5, 4, 3, 2, 1, 0. What is the length of this? This is 5. That's 6, 7, 8, 9, 10. Right? Length 11. Okay? Given length 11, if this is unconstrained, there's no way I'm going to get 0 here, 0 there, 0 there, and 1 there. Right? My design freedom is half only. Half in the sense that I have no freedom on this one, right? At exactly 0. Okay? I have no freedom over this, and so on. So, in fact, they have to be related. I cannot choose some arbitrary. And so on here. Okay, so the point I'm going to make is we want to find the condition on omega P, omega S, and its weighting, such that we guarantee to have 0, 0, 0, and so on and so forth. If you choose some arbitrary, there's no way to enforce this 0. Is that clear? So your design freedom is limited by a factor of 2 because you don't have the whole design freedom here. You have half the design freedom because the other one is 0. Okay? So I'm looking for frequency response, right? So I'm going to work with frequency over here. Okay? So how does P naught of Z related? So I know that P naught of Z minus Z is 2 Z to the minus L. Remember, this is one of the PR conditions that we derived log yesterday, right? And we deduct that P naught is a half band filter. You can show that if P naught satisfies this condition, then that is a solution. We derived that yesterday. Okay? I want to start from this property, look at the Fourier transform, and figure out how omega P and omega S are related. That's how we do it. Design meaning that start from frequency response, right? Constraint and find P naught of n. So we have to start with frequency. Okay? So frequency is Z. So I have P naught of e to the j omega minus P naught of e to the okay. So this is a shift in frequency. It's 2 e to the minus j omega L. What's next? So how do we use linear phase? Linear phase implies what? What is P naught of e to the j omega? If it's linear phase, how can I write this? There'll be a phase term, right? And there'll be an amplitude response term. Is that clear? Right. Linear phase is symmetric. I can factor out half the phase. Factor out the phase, right? And then what is left? It's sum of both sides. You need to remember how to do this, right? How do I find the phase response and the amplitude response of this system? If you look at this, what do I see? I see that if I factor out this L omega, what is left is a constant. Basically, I'm shifting this back to 0. Right? Factor out phase is shifting this response back to 0. Right? It's equivalent. Right? Is that clear? So what I see here is if I shift this back to 0, what do I get? A constant. This gives me what? E to the minus j omega, e to the plus j omega. What does that give me? 2 cosine. Yes, cosine, 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 so on and so forth. Okay? So you see that the phase response is exactly the center of symmetry. What is left is sum of cosine. Right? I'm going to call that, for shorthand notation, P of omega. Or P omega as sum of cosine. Right? It's basically 1 plus 2 times this, cosine omega, 0, 2 times this, cosine 3 omega, and so on and so forth. And the index for omega is basically the distance from the center of symmetry. Right? And you have 0 omega, 1 omega, 2 omega, 3 omega, and so on and so forth. At the end, you have L omega, because you have 0 to L. Is that clear? I'm grouping all of that into an expression they call P of omega. Now it's only a function of omega. This is basically no phase in here, right? Okay? It's a real quantity. And this is a direct property of linear phase system. Is that clear? So what I'm going to do next is I'm going to take this and plug into this. Right? So far, this is arbitrary. I'm going to constrain this on this. Okay? Let's take a short break. When we continue, we'll take this form and plug it to here and see what happens to P. Use this property of linear phase system, linear phase filter, in the half band properties, right? Remember that one is linear phase property. We're going to constrain this form by substituting this into here.